Okay, so today we're going to move on from electronic spectroscopy and talk about Fourier transforms, a little bit of crystallography, and get started on NMR. So somebody asked, where are we in the book at this point? So we're skipping around a lot, that happens. There is a special section on Fourier transforms. I don't remember where, but it's written on the syllabus. So if you check out the reading assignments on the syllabus, we're a little behind relative to the schedule that I posted. That's okay, that happens. But the part that goes with the Fourier transforms is it's like a little special math section. We're going to talk about crystallography briefly. That is in chapter 9. There's a whole chapter on solids. You can read it if you want. It's interesting. Most of what's in there is pretty descriptive. You know, it's nice to know, but there's not a lot that we're going to do with it in terms of problems. And then, hopefully at the end, we'll see if we get there, we're going to start talking about NMR. And that is, I believe, chapter 12. Okay, so let's get started talking about Fourier series and Fourier transforms. So how many of you have seen Fourier series and Fourier transforms before? Quite a few, okay. So this will mostly be review, but if not, as always for such topics, I recommend the Wikipedia page and the Wolfram website on Fourier transforms and Fourier series if you need extra practice. Okay, so a Fourier series is basically a bunch of sines and cosines that we can use to approximate other functions. And this works best if you have a periodic function, but it works pretty well for a lot of other things also. The main thing is you want it to be continuous in order for the function to converge, but it actually does work pretty well for things that are piecewise continuous as long as the function and its first derivative has those properties. Okay, so here's what this looks like. So our function, whatever arbitrary, hopefully periodic and continuous function is, converges to this series as you take an infinite number of terms. And it's just a combination of sines and cosines. And you know, when you first look at these, it seems kind of strange that you could have something like a square wave that has sharp corners and things and have that approximated by sines and cosines, but it works pretty well if we get a large number of terms in the series. Okay, so we have these coefficients A and B, and here I've just I've written down the definition of A naught. So A is the cosine terms, and B takes care of the sine terms. And of course, you need both because we have odd and even functions. And so you need the sines and the cosines in there. In some cases, one or the other is going to drop out. And we can use these things to approximate all kinds of functions, even things that are not periodic, even things that you wouldn't think this would be a very good approximation to. And this turns out to be really important for a lot of things in physical chemistry. So when we talk about NMR, you know, the explanation of NMR that's given in some intro texts treats it like other spectroscopy, where you say, okay, we sweep through the frequency and look at the response. That's how the early NMR experiments were done, you know, very, very early on. But the field's been around for 50 years. A lot of stuff has happened. At this point, basically everybody does Fourier transform NMR. So, you know, we're going to give a pulse, perturb the system, and get back a time-dependent signal, which we are going to Fourier transform and put in the frequency domain. This also comes up in IR spectroscopy. FTIR is very common. You've probably used these instruments in organic lab or in your research. As we're going to see in a minute, it's also really important in crystallography. The information that you get from a diffraction pattern is in reciprocal space, and you have to Fourier transform it to get the spatial pattern of the crystals. Yes? Mm-hmm.
Why in your AN equation do you have n start at 0 when up there you have the series start at n equals 1 in your Fourier series?
Well, so A starts at 0 and B starts at 1.
Yeah, but then in the series you have the series n equals 1 to infinity.
Well, so A0 is a separate term because you have to divide it by 2. Otherwise, yeah, otherwise it, go check out the Wikipedia page. But yeah, A0 is listed separately because there's this factor of 2 there. Okay. So let's look at an example. So here's a square wave. It's something that doesn't really look like it's very well approximated by sines and cosines because it has a lot of sharp corners, but it is periodic over the interval that we're looking at. And we can use this Fourier series to describe it pretty well. Okay, so its period, the way this is defined is 2t0. So, you know, that just means we're looking at this function, and if we wait 2t0, the value of it comes back to where it started in time. And we can also define an angular frequency with respect to that, and that's going to be important for our discussion of these kinds of time-dependent signals. So here's our Fourier series, and I'm plugging in the, you know, now we've got t and t0 because that's what we're summing over. And so we can plug this into the expression for the Fourier coefficients. And I know I'm going a little bit fast, but this is the same thing that we just looked at. We're just going to put it in for this function and evaluate it because it's pretty simple to do. And I will give you some practice problems on this and on NMR, hopefully today, maybe tomorrow. Okay, so we can look at the A series for this one and say, well, that's an odd function, so it goes to 0, which, as always, is a really good thing to be able to do. It saves us a lot of time. Okay, we still have to worry about the sign coefficients, though. Those are not going to magically go away. And so we can evaluate that. And just evaluating it for this function, here's what I get. So we can, in fact, sum up a bunch of sine terms for this square wave. And this picture on the right is what we get if we take the first 10 terms of this Fourier series. So you can see it starts to look pretty good. I mean, there are some little wiggles around the edges, and it's not perfect, but it starts to look like a pretty reasonable approximation. So we can use this for all kinds of things where it doesn't necessarily look like sines and cosines are going to be the best choice at just glancing at it. Okay, so now let's look at what happens if the function is not periodic. And of course, this is kind of important because, you know, we're going to talk about some applications in physical chemistry where the function is periodic over some time, but then it dies away. So for instance, an NMR signal relaxes, it's going to die out. You know, it is periodic over some time period, but not forever. And there are lots of applications in physics and chemistry and engineering where this is important. Okay, so if the Fourier series isn't periodic, that means that the period goes to infinity. So you have to wait forever before the function comes back around to where it was at the beginning. Okay, so in order to look at this, we need to start with the complex form of the Fourier series. So we can write that like this. So this is the same thing we were looking at before. It's just, you know, what you get if you allow these things to be complex numbers. And if you're confused about how I got from sines and cosines to an exponential, I definitely recommend checking out the Wikipedia page and the Wolfram site. Okay, so we can write down these coefficients in terms of this kind of an integral again. And again, we're defining our angular frequency omega naught in terms of the period tau. And so we're going to evaluate these coefficients. And to do that, we're going to substitute and use a dummy integration variable, which I'm going to call u. And I'm doing that just so that I don't get confused between the t in this integral and the t in this sum, which otherwise might cause some problems, because we have to evaluate that integral and then stick it back into the sum to get the answer. OK, so now I'm integrating that in terms of u. And I'm going to say, OK, what happens if the period of this function becomes very large? That means that omega naught, its frequency, gets very small. They have an inverse relationship. And so I'm going to call that delta omega. It's just a very small frequency. OK, so if I do that and plug my result back into the original sum for the complex version of the Fourier series, then I get something that looks like this, which I can evaluate. And we're still looking at this in terms of our dummy variable u. OK, so let's take the limit of that as our little frequency increment delta omega goes to 0. This looks like the Riemann sum definition of an integral. So we can just write this Fourier series as an integral. And this is an important result. So this is Fourier's integral theorem. And it tells us something about Fourier transform pairs that we can use. So as you can see from these examples, frequency and time make a Fourier transform pair. They have an inverse relationship, and we could use this kind of an integral treatment to look at them. So we usually call the one that's in the frequency domain big F, and the one in the time domain small f. And this is really useful because it allows us to go back and forth between frequency and time, or reciprocal space, which we get from a diffraction experiment, and real space, which tells us the crystal structure. This was a pretty amazing result for its time. So Fourier worked this all out. And if you look at his original work, it seems kind of ill-defined by our standards, just because when he was doing it, the definitions of a function and the derivative of a function and what it means for things to be continuous were really not well established. But it has held up well. These results were later formalized by other people, but the basic thing has stood up well. Question?
In the capital F of omega function, is it supposed to be an integral du as an exponent?
Yeah, that's a typo. The du should not be in the exponent. Good point. OK, so let's look at some Fourier transform pairs. And here, you would have to work this out to actually figure out what they are. But I'll just show you some examples. So if we have a complex exponential like this, in the time domain, the Fourier transform in the frequency domain gives us a delta function. So it's got a constant in front of it, and then we have a delta function. For something that looks like this, kind of an exponential, the Fourier transform of it looks like that. Let's look at some examples that are, more likely to come up in real problems. So if we have a Gaussian, so here's a Gaussian function. The Fourier transform of that is another Gaussian. And I want to point out that they have reciprocal relationships. So if you have a Gaussian that's very narrow in the time domain, its Fourier transform in the frequency domain will be really broad, and vice versa. And that's something that you should remember as part of your intuition about these things. Same thing in crystallography. If you have a really high resolution crystal structure, that means that your data go out really far in K space or reciprocal space. So if you have more spots extending out really far in K space, that means that you're getting really, really good resolution in real space. Same thing with an NMR signal. If we have a signal that goes on for a very long time in the time domain, that corresponds to narrow peaks in the frequency domain. So just to give you a visual idea of what these look like, here are some Fourier transforms of different objects. So you can do this in 2 dimensions or 3 dimensions or however many dimensions you want, really, which, of course, that makes sense when we're talking about something like a crystal structure that's 3-dimensional or multidimensional NMR spectra. But so here are what the Fourier transforms look like for some standard-looking objects. So you can see it's, you get some rounding out, and you get these periodic sort of wiggles at sharp corners, but you can see the relationships for the shapes. Okay, so here's a crystallography example. So this is from a relatively recent Nature paper where people were looking at gold nanorods, and they want to see what does the surface look like at the crystal structure kind of level. And here's their data on the top. So they have these patterns of dots that are based on the diffraction from the gold atoms. And these look really nice and sharp, especially if you're used to looking at protein crystallography data, because we just have these individual atoms. The electron density around it is really well defined. And also gold atoms have a lot of electron density compared to things like carbon and nitrogen and oxygen, the things that proteins are made of. So we see these really beautiful, nice, sharp spots. That also tells us that their crystal is really perfect. If we had a lot of mosaicity in the crystal, a lot of sort of scatter in the spatial positions of these things, we would see the spots being kind of blurred out and not as high resolution. But so, and in fact, in the middle picture, you can see a little bit of that. The spots are not as sharp as they are in some of the other ones. But we can see that this corresponds to these regular crystal lattices, but it's not giving you a direct picture. You have to take the Fourier transform, and there's a reciprocal relationship there. Okay, so let's go back to where we left off last time, talking about X-ray crystallography and how we can use this to get structures of molecules. So we just saw it with a really simple example where all we have going on is just a lattice of gold atoms. And so that's pretty easy to visualize how you Fourier transform that, the diffraction pattern, and see what the structure looks like. For something like a protein molecule, that's a lot harder. The unit cells are large, they're complex. The atoms that we're looking at don't have as much electron density, so there are a lot of things going on. So in order to get this data, first we need to grow a crystal. This particular one is lysozyme. That's a crystal that I grew, which anyone who's worked in a protein lab knows that lysozyme is really easy to crystallize. This is something that people use as a setup sample very often. And then this is not my data, neither is that. But when you have your regular repeating lattice of protein molecules, you can get X-rays to diffract off it. And again, the Fourier transform relationship tells us that if we have a lot of spots going really far out in the diffraction pattern. You know, so we're looking at you know, we're taking images of this crystal and tilting the sample a little bit. So we have a two-dimensional map of the diffraction, and then we get the third dimension by taking slices. You know, we tilt the crystal. If we have a lot of spots out here, that means it's a really high-resolution structure. If we got something where we just see, you know, something where we just have a few spots in the middle, that's lower resolution. An example of a relatively low resolution thing is this fiber diffraction pattern that was for you know, Watson and Crick's DNA structure. And one reason it's low resolution is because it's just a fiber, it's one-dimensional. So we see a lot of intensity out here in one dimension, that's where the fiber axis is. And then across the other way, we don't see a lot of intensity, so it's very asymmetric. Whereas for this thing, we have a perfect crystal, and so we see a lot of intensity in all directions. Okay, so here's what that looks like in 3 dimensions. So in order to get the electron density, I should be careful and not call it a structure yet. In order to get an electron density map from this kind of diffraction pattern, we have this density function, and we have to sum over h, k, and l, which are, that's the reciprocal space axes. So it's the inverse of x, y, and z. And so we take this, this kind of a Fourier transform, and we are able to get the spatial function having to do with the periodic crystal lattice from that. And again, here are some examples of simple crystal lattices. There's a lot of this stuff in Chapter 9. Of course, the ones that you want to look at for organic molecules or protein crystals are going to be much more complicated than that. We have different space groups. Okay, so again, here's a rundown of the process. So you have your crystal. It's a periodic lattice of molecules. We diffract X-rays off it, which we can do because electrons have some wave character. And because we have a repeating lattice, we get these nice diffraction patterns. And if we do, we can Fourier transform that, get an electron density map. And then you can see here the, how people go about analyzing these data. So this wireframe thing is the actual electron density map. That's the part that's experimental. And then you have to kind of use your imagination and fill in the particular protein side chains to then go ahead and get the structure. And I just want to show you an example of that you know, that was used to solve the structure of an interesting molecule. I'll show you some examples of NMR structures when we get there too. But here's one where you can really see the electron density, and it's a nice high-resolution structure, and it looks very convincing as far as what's in there. Unfortunately, not all of them are that high resolution, and it's not as obvious what's going on. But this particular example is from Roderick McKinnon's Nobel lecture. He got the Nobel Prize for solving the structures of some of these ion channels. So this particular one is a potassium channel. It selectively lets potassium come through and keeps sodium out. So it's got a selectivity filter, and then it has these dipoles in here where there's a specific size, and you see the, you know, the part of the helices, you know, these carbonyls are oriented toward these ions, and that can shuttle the ions through. And this thing can undergo conformational changes depending on how much potassium is around it, such that these helices are either closed like this, or they open up when the channel is working and it's transmitting potassium. And so, you know, again, here's what that looks like. It has 2 conformations. It can be collapsed, where this part in the middle is shoved together and there's no room for the ions to go through. And it can be open and conducting these things. So I just want to show you an example where looking at the structure of the molecule really tells us a lot about its function. And you can see here in these electron density maps how you can measure directly from looking at that electron density where the ions and the parts of the molecule are. Okay, so let's move on to talking about pulsed NMR. And we're going to go through different aspects of this, and we're going to talk about some things that aren't in your book. So the description of NMR in the book is a little bit like the organic chemistry view of it. So there's a lot of descriptive stuff. How do you tell the structures of molecules given an NMR spectrum? And that's important. It's a good thing to know how to do. But I also want to get into a little bit more detail about how it actually works in the quantum and spectroscopy sort of sense, because this is P-Chem, and we should get into a little bit more detail than just the descriptive part. Also, I should point out that since I'm an NMR spectroscopist, that's the thing that you're going to happen to get a lot more detail on. If this were being taught by someone who does IR spectroscopy for a living, it would probably be different. But that's the joy of having a bunch of different professors who do research for classes. All right, so let's look at how pulsed NMR works. So depending on sort of the level of detail that was gone into in your organic chemistry class, you might have heard different things about how NMR works. So one description is the CW description, where you sweep the frequency and get different responses from the molecules when you put the nuclei in a magnetic field. Again, you can do that, it works, but it's outdated. That's not really what people do. So in a typical NMR experiment, the way it's conducted in a modern instrument, we have our sample in the magnetic field, and all the spins line up either against or with the magnetic field. And as we'll see a little bit later, that's not strictly true, but it's an approximation. And when we pulse the sample, so we have our spins, there's a net magnetization vector of spins pointing with the magnetic field. We pulse the sample and put them into the XY plane. So we had the spins oriented like this. Now we have them oriented like that, perpendicular to the field. That means we change the quantization axis of the system. But for now, we can just approximate it as these little vectors. And so what happens if I release that pulse that's keeping them perpendicular to the magnetic field is that the magnetization vector is going to return to equilibrium. It's going to come back to the starting point. But of course, it doesn't go straight back because the spins are precessing about the main magnetic field. So it has this periodic sort of character as it comes back. And of course, my detector is in the XY plane. So I have a detector along the X and the Y axis because I'm collecting the real and imaginary parts that are orthogonal to each other. And so as I'm looking at this signal in the XY plane, I'm going to detect a periodic function. And so here I've represented that as just perfect sines and cosines because I'm neglecting the relaxation just for the sake of simplicity. But hopefully what I want you to get out of this at this point is just that, all right, our detector is in the XY plane and it's picking up a signal. So what that looks like with relaxation is you have that periodic function, but now we've put an exponential decay onto it. Because of course, I have maximum signal when I start out in the XY plane, and then the magnetization is going to go back up to equilibrium, and that's where this exponential decay comes from. Then if I Fourier transform that, so this is my time domain signal. If I Fourier transform that, I get what's called a Lorentzian. If I'm lucky, sometimes these peaks look more Gaussian in shape. But so here's my f of t. And so as you'd expect, I've got an exponential decay and then a cosine function. I start with maximum signal, and then it decays and has this periodic character. If I Fourier transform that, here's what my function of frequency looks like. It's called a Lorentzian. And in a realistic NMR experiment, I can neglect this term. I'm just going to take the first term. And so this is the function for my NMR signal. Okay, so you might ask, why do we have to do all this Fourier transform stuff? We have a perfectly good function that we can fit, and we know what its functional form is in the time domain. Why not just use that? Like, why don't I just analyze this cosine function? It seems reasonably well behaved. The reason is that these things look messy when we have a whole bunch of different frequencies, like in a typical NMR experiment for a complicated molecule. Okay, you have seen this before. I'm just putting it in a little bit different terms. But same thing. So here S of t is the NMR signal, and we're obtaining it by measuring it directly. And then if we Fourier transform that, we get a function of nu, which is the spectrum. Okay, so let's say that we have a complicated molecule. It's not even very complicated in this case. We have 4 different frequencies going on. You know, of course, if we're looking at nuclei that are in a real molecule, they're going to have different chemical shifts or different resonant frequencies depending on their local environment. Of course, their local environment mostly depends on the magnetic fields around them, which are produced by the electrons, which of course are in the chemical bonds. So that's why NMR is so useful to us as far as determining the chemical environment of things. But if we add up all of those different frequencies, you know, even in this case where we only have 4, we get a time domain signal that looks really messy, and it would be extremely hard to interpret. So that's why we don't do it. If we Fourier transform this, then we pick out these signals in the frequency domain, and here they're drawn as delta functions. Of course, for a real signal, they're going to have this Lorentzian line shape, and they'll have a width that's inversely proportional to the length of the time domain signal. But you know, here we're drawing these as perfect periodic functions. So again, here's another example that has 3 peaks. And you can see the time domain signal is a mess, and you don't want to interpret it. So Fourier transforming it and looking at it in the frequency domain is the way to go. OK, so what I'm going to do now is back up and talk about the physical basis of NMR and how that works. You know, now that we've talked about the Fourier transform and how we process the signals. We're going to be coming back to this a little bit later. I just wanted to introduce it. Does anybody have any questions about this part before we go on? Yes?
Is there any quick explanation as to why we can ignore the second term of the Lorentzian?
So why do we ignore the second term in the Lorentzian? I'm going to give you a lame explanation. I'll try to think if there's a way to say the real explanation concisely for next time. It's basically off resonance with the effect that we're looking at, so it doesn't have a very big effect. It does come back and bite you sometimes. It is not a good approximation that you can leave it alone in all NMR experiments. Just for most things that you do in the context of looking at structures of molecules, that's a fine approximation. I feel like there was something else I wanted to say about this. OK, yeah, I just wanted to mention that we're skipping chapter 9, but if you're interested in the crystallography stuff and things about solids, there's a bunch of good stuff in there. So I recommend reading it if you're interested. But as far as what we have time to do, that's basically going to be it for chapter 9 and solids. OK, so let's back up and talk about the physical basis of NMR. And in fact, for the moment, I'm just going to talk about physics of electrons. So we know that electrons have spin 1/2. And we know that they behave as fermions, and they pair up, and all of these things. Let's back up and talk about how we know. So the Stern-Gerlach experiment was the original demonstration of electrons having spin. And this was done in 1922. So what they did is they had a bunch of silver atoms, and if you remember, electron configurations from general chemistry, silver atoms have one unpaired electron. So, the rest of them are the rest of the electrons are all in a closed shell, so they're not really contributing anything to the effect. We're just looking at the effect of that one unpaired valence electron. And what they did is they heated up a bunch of silver in a furnace so that they had a bunch of the atoms coming out in a vapor. And then they ran that beam of silver atoms through an inhomogeneous magnetic field. So we've got, a magnet where it has sort of a funny shape, and so you can see the field lines sticking out here. They're not homogeneous. And instead of having this beam just kind of spread out like this and give one spot that's messy, it actually splits. And so nobody understood this theoretically until 1925. So this experimental result was published. And, hey, if you put these atoms through an inhomogeneous magnetic field, you get two spots on the detector. Nobody knows why. This was just sitting out there in the literature. And then this was explained in 1925. So let's look at the classical and the quantum explanations for this. OK, so we have our potential energy for this in classical terms. And we can say before the atoms go through the electromagnet, their magnetic moments are completely randomly distributed. So we're approximating the electrons as looking like little bar magnets. And if there's no magnetic field, they're just randomly distributed in space. And we can calculate the force, which would be 0 if the field were homogeneous, but it's not. And so to do that, we need to take the gradient. And we can also look at the total moment relative to the position of the atom. And so, here, what's gamma? That's the gyromagnetic ratio, in this case, of the electron. And so what we see is that dl dt is perpendicular to L, and the angular momentum of this atom is precessing around the magnetic field. And so to find the force, we're going to use some approximations. So we're going to say that mu x and mu y are 0. So this thing is precessing around the magnetic field, which we're going to call z. And so the x and y components cancel each other out. And mu z is basically constant, because we're precessing around the main magnetic field. And so our force is just going in the z direction. And so when we go to take the gradient, we know that the partial derivatives with respect to x and y are 0. And so the force that's causing our deflection of the little electromagnets is parallel to the z-axis, and it's proportional to the magnetic moment in the z direction, which makes sense. And so if we measure that deflection distance, that's where these spots are relative to straight through, that's indirectly measuring our angular momentum along z, or the z magnetic moment. And so here's what you get when you do the experiment. And I wanted to show the original data because a lot of times when we're talking about these classic physics experiments, we look at really stylized presentations of how it works, and it makes it seem really beautiful. It's not that way. This is kind of messy, and it's it's hard to interpret. So this is the original data. The beam is actually split. So here's without the magnetic field, and then with the magnetic field, it's split with a minimum in the center. So it's not nice and clean and perfect, but you can tell that it's going on. And if we look at this in the using the quantum picture, which it turns out that we need to figure out what's going on, we already know that measuring this deflection distance, so how much these, the position of these atoms deviates from the expected classical result, that is measuring LZ or mu z. We need a quantum observable to go along with LZ, the z angular momentum. And so we call it IZ. So this is one of the postulates of quantum mechanics, right, from last quarter. So for every quantum operator, you need an observable to go along with it. And this observable has two non-degenerate eigenvalues. It's in increments of h bar. So we have, it's plus or minus h bar over 2. So if we look at this and compare the classical and quantum pictures, so in the classical sense, our energy is just minus mu dot b. And we can write this down as a quantum Hamiltonian, you know, where we're using h to represent the energy, and then we're replacing mu with our quantum mechanical operator mu. And then we see that the magnetic moment is proportional to the angular momentum. So now here's our angular momentum observable I. And we get this constant out, gamma, which I said is the gyromagnetic ratio. And that's, you know, this is a fundamental constant that has to do with the particular type of spin that we're looking at. So this one is for electrons. We'll see that nuclei have different gyromagnetic ratios. And so here's what we get here. We see that when a magnetic field is applied, we break the degeneracy between values of plus and minus 1/2 for the electron spin. So you can think about this, you know, in the classical sense as saying having the electron aligned with the field is a lower energy state than having it aligned against the field. And again, when we actually do this, it doesn't mean that all the electrons either align with or against the field exactly. There is still a distribution. It's just that that's all you can measure. You can only measure these two states. These are eigenvalues of this particular Hamiltonian, and that's all we can measure. And we will talk a little bit more about what that means next time. So we break the degeneracy. We raise the energy of the upper state by 1/2 these constants times b naught, and then we lower the lower energy state by the same amount. And this whole thing, you know, this effect of splitting the energy levels for electrons or nuclei that have spin greater than 0 in a magnetic field is called the Zeeman effect. Okay, so let's look at the gyromagnetic ratio a little bit more closely. So this has to do with the charge on the electron and its mass. And so for a magnetic field along the z-axis, we're going to call it b naught. Here's the Hamiltonian for that electron. So we have this constant that has to do with some fundamental properties of the electron. And then it depends on b naught and depends on, and then we have this observable IZ. The eigenvalues of IZ are m sub L times h bar, so that's where we get this plus or minus 1/2. And here's the expression for mu z in this case. And we can also write down the energy of interaction in terms of the gyromagnetic ratio, the m sub L value times h bar, and the magnetic field. And one thing that you learn from this is that if we want to get a big energy separation between plus and minus 1/2, you know, in order to measure these effects, it's going to work better if you have a big magnetic field. And this is definitely related to why people want bigger and bigger NMR magnets. You know, same thing goes for EPR to a point, although there are challenges in working with high field there. let's, so this tells you about the basic effect, what's going on with the Zeeman interaction. How do we map the classical energies onto quantum observables in terms of things that we know how to deal with? And we have been talking about angular momentum a lot in the sense of, you did it last quarter talking about orbital angular momentum, for electrons within atoms. We also talked about it in the context of rotational spectroscopy. Here we're going to look at it for spins of electrons in nuclei. So here's an example of how electron spin is used in its interaction with magnetic fields. So this is how a cyclotron works. We have a beam of electrons that gets shot through a big magnetic field, and these are usually made with arrays of permanent magnets at this point. And the magnetic field bends the path of these charged particles, the electrons. And when you do that, X-rays get emitted. So we have really high energy X-rays. So this is where a lot of the experiments for a lot of the early high energy physics experiments came from. The first one was at LBL in Berkeley. And here's another demonstration of the electron Zeeman effect from an astronomy example. Sunspots have really strong magnetic fields. And in this picture on the right, you're seeing a natural example that's taking place in a sunspot of Zeeman splitting. This thing where it's split into 3 is from a transition into a p orbital for electrons within the sun. Okay, so this also works for nuclei. Some nuclei have spin greater than 0. So in the NMR context, for organic molecules, we mostly look at protons and C13 and N15, which fortunately are all spin 1/2. That makes it easy to study some of these molecules. Of course, the most common isotopes of carbon and nitrogen have spin 0. That's carbon-12 and N14. Yeah, I just made a mistake. N14 does not have spin 0. It has spin 1, but it's difficult to see. In any case, C13 and N15 are spin 1/2, which means they have 2 orientations with respect to the magnetic field, and that makes things easy to look at. Since protons are also spin 1/2, we can use exactly the same treatment. So there's nothing new here, because we're just talking about nuclei instead of electrons. But I do want to point out a couple of things just in terms of terminology. So one is that we have the plus 1/2 eigenvalue, which is being called alpha here, and minus 1/2 is beta. And we're going to use this throughout when we talk about NMR spin states. So alpha and beta are just nicknames for the up and down states of a spin 1/2 nucleus, and we will see them a bunch. Note that alpha does not equal minus beta, and we call these things wave functions, but in the NMR wave functions, this is kind of a funny description, right? Because it's not, we're used to the wave functions being something that looks like a real function. So we have the Hermite polynomials for a harmonic oscillator or spherical harmonics for a rigid rotor. The NMR wave functions are just, they're functions in the sense that it's a probability mass that's all on one value. So if something is in the alpha state, that just means that it's in the state where its eigenvalue is plus 1/2. If it's in the beta state, it's in the state where its eigenvalue is minus 1/2. What that function is not something that's well defined in terms of these other things. It's kind of a delta function where all of its probability mass is on that one state. The other thing I want to point out is that we're going to be talking about NMR, nuclear magnetic resonance. The resonance condition is when h nu, our incoming radiation, equals gamma h bar b naught. So we mostly think about the main magnetic field when we talk about NMR, but that part's boring. That's just lining up the nuclei. The part that we need to perturb them with is the radio frequency field that we're putting in to flip the spins and change their quantization axis. So that's an introduction to the conceptual part of NMR, how it works. We're going to talk about it a lot more next week. But I think Monday is a holiday. Is that true? Yeah. Happy President's Day, everyone. I will see you on Wednesday.